Students, in third unit, so far we have seen frequency domain specifications, the correlation between frequency domain specification and time domain specification, and we have seen what is meant by Bode plot and various Bode plot shapes for simple transfer functions such as g of s is equal to k into s, g of s is equal to k by s, g of s is equal to k divided by 1 plus s into capital T. So for such simple transfer functions, we have seen the approximate Bode plots. Okay. So with that knowledge, in this video, we will be telling you how to compute frequency domain specifications such as gain margin and phase margin from the Bode plot. Okay. So that is what is the objective of this video. So now let us get into the session. Students can take a semilog graph sheet with them so that as I say, they will be able to do that in the graph. Okay. So to get the gain margin and phase margin, first step that we have to do is we have to do the Bode plot. To draw the Bode plot, we have to obtain the magnitude of the open loop transfer function and phase of the open loop transfer function for various frequencies. Okay, for various frequencies, they have to get magnitude and phase. Tabulate it and keep it. After tabulating it, please draw the curve. The first curve should be magnitude versus frequency. You can have the frequency x-axis as common, and you can split the semilog graph sheet into two. That is, in the upper half you can draw the magnitude plot, in the lower half you can draw the phase plot. Magnitude plot is between magnitude of open loop transfer function in dBs versus frequency. This is your magnitude plot. And another one will be phase of open loop transfer function with respect to your frequency. So two plots you will get. After drawing the two plots, we will obtain the gain margin and phase margin by computing gain crossover frequency and phase crossover frequency. Okay, so the next step is to get the gain crossover frequency and phase crossover frequency. The frequency at which the gain is 0 dB is called as gain crossover frequency. So that means from 0 dB, you draw a straight line to cut the magnitude plot, and the corresponding frequency is called as gain crossover frequency. The definition is the frequency at which the gain of the transfer function is 0 dB. That means from 0 dB, cut the magnitude plot, see the corresponding frequency. That frequency is called as gain crossover frequency. Okay. And phase crossover frequency is nothing but the frequency at which the phase is minus 180 degree. So that means from minus 180 degree line, you please draw a straight line to cut the phase plot. The corresponding frequency is called as phase crossover frequency. So again I repeat it, from minus 180 degree, you please draw a straight line to cut the phase plot. The corresponding frequency is called as phase crossover frequency. So after finding gain crossover frequency and phase crossover frequency, now we will move on to find gain margin and phase margin. So gain margin is nothing but start from phase crossover frequency. Okay. The gain corresponding to phase crossover frequency is what is required. That means from phase crossover frequency, please look at the magnitude plot. Draw a line to the magnitude plot. See where it cuts. This point it cuts. The corresponding magnitude. The corresponding magnitude has to be noted, and that magnitude has to be negated to get the gain margin. Okay. Suppose I start from here, omega PC. This line cuts the magnitude at this particular point. See what is the magnitude. If it is minus 6 dB, minus of minus 6 dB is plus 6 dB. So gain margin is 6 dB. Because gain margin's definition is minus 20 log of G of j omega at PC. At PC, that is phase crossover frequency. So I am starting from here, going to the gain plot, seeing what is the magnitude, negate it. I will get the gain margin. So coming to phase margin, you start from gain crossover frequency. The phase corresponding to gain crossover frequency. That means start from omega GC, go to the phase plot that it cuts here, see the corresponding phase. That phase is called as phase at gain crossover frequency. Phase at gain crossover frequency 5GC. Okay. So after obtaining this, add it with 180 degree to get the phase margin. Phase margin gamma is equal to 180 degree plus 5GC. So that is the definition for phase margin. So once you get the 5GC, add it with 180 degree, you will get the phase margin. Suppose here I start from omega GC, it cuts the curve at this point, the corresponding phase, let it be minus 120 degree. Okay, somewhere here minus 90 degrees there, here minus 180 is, let us take this point as minus 120. 5GC is equal to minus 120 degree. So phase margin is equal to 180 degree minus 120 degree, that is 60 degrees. Phase margin you will get it as in positive, uh, that is plus 60 degrees. Okay, so this is how you find the gain margin and phase margin. The same thing is repeated here, but only thing is the curve shape is slightly different. This is another example. Okay, this is another example where you can see that phase crossover frequency comes first, then comes your gain crossover frequency. Okay, that means omega GC is greater than omega PC. Here you can see that omega GC is greater than, sorry, omega PC is greater than omega GC. Okay, so here also same procedure you have to repeat it so that you get the gain margin and phase margin. So to get gain crossover frequency, you have to start from 0 dB line. That 0 dB line cuts the gain graph at this point. The corresponding frequency is called as gain crossover frequency. For phase crossover frequency, from minus 180 degree, you have to draw a line to cut the phase plot, and the corresponding frequency is called as phase crossover frequency. So now from phase crossover frequency, you have to see what is the magnitude of the magnitude plot corresponding to phase crossover frequency. That is, draw a line from omega PC, go hit the magnitude plot. The corresponding magnitude has to be noted. Of course, here the magnitude seems to be in the positive. Suppose this is 12 dB, then your gain margin is minus 12 dB. Okay, so you are getting your gain margin in negative now. And for phase margin, start from omega GC, hit the phase plot. Actually, the phase plot is hit here. You have to draw a dotted line here only, slightly below what I have drawn. So it hits here, and you come and see what is the phase. The corresponding phase will be your 5GC. Okay. After getting 5GC, you add it with 180 degree to get the phase margin. Okay, so now if you look at the phase, somewhere it falls between minus 180 and minus 270. So let me take it as minus 220. So what will be your phase margin now? Phase margin is equal to 180 degree minus 220 degree. So your phase margin will be minus 40 degree. Okay, so negative phase margin now. Now it is negative phase margin. I repeat once again, from gain crossover frequency, draw a line to phase plot. It hits here. The corresponding phase has to be noted. Okay. If you know at this particular point, actually this line has to be this point you note down the phase. If it is minus 220, add it with 180 degree, you will get the phase margin. So with this knowledge, let us move on to a particular problem. So now this is the problem given. For the transfer function given, we have to draw the Bode plot and obtain the gain margin and phase margin. Okay. So now if you look at the transfer function, it is in the standard format. What is the standard format? Every term should be in the form of 1 plus s into a constant. So if you look at this transfer function, it is in the standard format because 1 plus s into capital T. 1 plus s into capital T. There are two time periods, 3 and 4. So you will have two corner frequencies. One is 1 by 3 and another one is 1 by 4. Okay. So there are two corner frequencies, omega C1 and omega C2. So which is lesser? 1 by 4 is lesser. So I am taking 0.25 radians per second as the first corner frequency, and 1 by 3 is 0.33 radians per second. So I am taking that as the second corner frequency. Okay, so there are two corner frequencies for this transfer function. Now we will get the magnitude equation and phase equation for this transfer function. For 20, the magnitude is 20 and the phase is 0 degree. So I have given the magnitude 20, there is no phase for it. And for j omega, now this g of s has to be replaced by j omega. So you will get j omega 1 plus 3 into j omega into 1 plus 4 into j omega. For each and every term you have to find the magnitude and phase. So for j omega, magnitude is omega and phase is minus 90 degree because j is in the denominator. So minus 90 degree. For this term, you will get magnitude as square root of 1 plus 9 omega square by using the formula square root of a square plus b square, which is the magnitude of a plus jb. Am I right? So using that, you will get magnitude as square root of 1 plus 9 into omega square, and phase is tan inverse of b by a, that is tan inverse of 3 omega by 1. Since it is in the denominator, it is minus tan inverse of 3 omega. And for this term, 1 plus 4 is magnitude is square root of 1 plus 16 omega square, and the phase is minus tan inverse of 4 omega by 1. So now you got magnitude equation and phase equation. Now our job is to get the various values of magnitude and various values of phase for different frequencies. So the choice of frequency is now a question mark. The choice of frequency should be, you have to compulsorily take the corner frequencies as your choice, that is 0.25 and 0.33. So I have taken 0.25 and 0.33. Other frequencies, it is up to you. You have to choose a frequency lesser than this first crossover frequency and a frequency greater than the highest corner frequency. Okay. So I have chosen it as 10 times lesser so that the graph is easy for us to draw in a semilog graph sheet. So I have taken it as 0.025 radians per second. Okay. And a frequency greater than 0.33, I have taken it as 3.3 radians per second. So for four frequencies, I am going to compute the magnitude. That means I have to substitute now for omega 0.025 here. Okay, please take a calculator and substitute 0.025 here and find out the magnitude in decibels. Approximate decibels are here 58.06. Then substitute 0.25 radians per second. You have to get 38. For 0.33 you are getting 33, and for 3.3 it is minus 27. Okay. And for phase, the phase curve has to be little bit smoother than this magnitude curve. So you can choose some more points also, like points between 0.25 and 0.33, points between 0.025 and 0.25. Some extra points you can choose because the curve will look smoother. Okay, whereas magnitude plot, it's not necessary that it should look smoother. Whereas for phase plot, if there are many points, then the curve will be little bit smoother. So I have chosen here even 0 radians per second and something like infinity also. Okay. So tan inverse of omega, if you give infinity here, it will be minus 90, minus 90, minus 90. So minus 270 degree. Okay. So other frequencies, you please substitute here 3.3 radians per second here and find the answer in degrees. So these answers are in degrees. Okay. And these omegas are in radians per second. So for 0.33 I am getting minus 188, 0.25 minus 172, 0.025 minus 99. Okay. So for 0, if you substitute here, you are left out with only minus 90. So for 0, it is minus 90 degree. So you got the phase values for different frequencies. So now you can go to a semilog graph sheet and you can draw these two curves. Okay. So I have drawn the graph here. This particular see, you know that this is a semilog graph sheet. Okay, so first point, if you take it as a point not 1, then the second one will be 10 times, that is point not 1. If this is point not 1, then the next one will be point 1. If this is point 1, and the next one will be 1. Okay, if this is 1, then the next one will be 10. Okay, so the frequency should go in like in multiples of 10. Okay, so depending upon these frequency values, I have chosen the x-axis. So I want a point not 25, I want a point 0.25, okay, I want a point 3.3. So I have chosen it like this. So this point will be point not 1, this is point not 1, this is point 1, 1 and 10 radians per second. Okay, so 4 points I have plotted here. See, now I have allocated the upper portion for magnitude graph and the lower portion for phase graph. Okay, so please divide this graph into two. The upper is for magnitude. The magnitudes are in the range of, I'm getting even minus 27 and even plus 58. So okay, so this is 0 dB line, this is 20, 40, 60, minus 20, minus 40, minus 60. Okay, 1 unit in this graph is 20 decibels. Okay, and in phase graph, all the phases are in negative. So to cover the range of phases that we are getting here, okay, so it is ranging from minus 90 to minus 270. So I have chosen uh, every unit as 50 degrees. Okay, minus 50, minus 100, minus 150, minus 200, minus 250, minus 300. Okay, so this portion is for phase plot. The lower portion is for phase plot. This x-axis frequency is common for both magnitude and phase plot. So the first point is 0.025, okay, and 58 dB. So 0.025, where it will come? This is 0.01, am I right? So this will be your 0.02 and this will be your 0.03. So in between 0.02 and 0.03 you will have 0.025. So I have taken that point and the magnitude is 58. So here I think this line is 58. So we have taken that and this is the point. Okay. Likewise, please do it for all other 3 points. And then using a scale you can join it. Okay, so that the slope is very clear. I have taken a scale to draw this. Okay, this is not a smooth curve. So this is your magnitude plot. Okay, and phase also similarly. For the same point not 25, what was the degrees? Minus 99. Okay, approximately 100. So here it is. Same point not 25 frequency. The phase is minus 99. Very much closer to that 100 point. So here it is. Okay. Similarly, please plot the other points also, and kindly join all these points using a smooth curve. Okay, the phase plot can be a smooth curve. This is your phase plot. Okay, so after completion of this video, please you draw by yourself and see, okay, whether you're getting this curve. So what's our job now? We have to find the gain crossover frequency and phase crossover frequency. With the help of gain crossover frequency and phase crossover frequency, you have to find the gain margin and phase margin. Okay. So now let us find the gain crossover frequency. From 0 dB line, you hit the magnitude plot. Okay. What frequency is this? this point is at what frequency? Okay, this point is at please look at the frequency. It is, see here, since the in the upper line I have written the frequency, I am going up to see the frequency. It is 1.1, this point. Okay, this is at this particular point the frequency is 1.1 radians per second. So gain crossover frequency is 1.1 radians per second. Okay, and phase crossover frequency, you have to draw a line from minus 180 degree. Where is minus 180 degree? Of course this line is minus 180 degree. Come here, hit the phase plot. At this point, what is the frequency? Please go up and see. I think the frequency is 0.3 radians per second. Okay, the frequency is 0.3 radians per second. So phase crossover frequency is 0.3 radians per second. Okay, so now we have got omega GC and omega PC. Okay, so for gain margin from this omega PC, the magnitude corresponding to omega PC. Okay, am I right? So the magnitude corresponding to 0.3 radians per second, that is nothing but minus 32. Since I have already drawn here the line, so it is minus 32 dB. How to find it? From this particular, this is the frequency. The violet color line is nothing but the frequency 0.3 radians per second. Am I right? That 0.3 radians per second corresponding magnitude from 0.3, the corresponding magnitude is minus 32 dB. So gain margin is minus of minus 32 dB, that is 32 dBs. Gain margin is 32 dB for this problem. So for phase margin, we have to start from omega GC. So omega GC is 1.1 radians per second, am I right? So the phase corresponding to this 1.1 radians per second is, if you come and hit the phase plot and see what is the phase is minus 240. Okay, this minus 240 is the phase corresponding to what frequency? 1.1 radians per second, that is omega GC. So 5 GC is minus 240. Your phase margin is 180 degree plus 5 GC. So you got phase margin as minus 60 degree. That's it. So maybe at the first attempt, it might not be that easy for you. You can practice it in a semilog graph sheet. It becomes very easy. Okay. Now you can practice it in a semilog graph sheet. You draw the two graphs, find the two frequencies, and find the gain margin corresponding to phase crossover frequency, and phase margin should be found from the gain crossover frequency. That's it. Okay. So try this problem now in your semilog graph sheet. So you can try it, and now let me give you another problem also. I have solved this problem in this video. Okay, but you take your own time to do it. Okay, so this is the transfer function, and these two are the cutoff frequencies. This is the magnitude phase. I have chosen some frequencies, that is frequency lesser than the lower cutoff frequency and frequency greater than the upper cutoff frequency. That is your choice actually. Even it can be 20 or 100. Here I have taken 10, 50. It can be even 100. Okay, so that it's 10 times greater. So after getting all the frequencies, you have to substitute the frequency in a magnitude equation and phase equation to tabulate magnitude versus frequency and phase versus frequency. Convert all these points to semilog graph sheet. Okay, I have converted all these points to semilog graph sheet. From this, the question is actually we have to find gain crossover frequency and phase crossover frequency. So it's very easy. From 0 dB, you have to cut the magnitude plot, and the corresponding frequency is your gain crossover frequency, that is 5 radians per second. Okay, I think it comes to 5. And the phase crossover frequency is nothing but from minus 180 degree, you have to hit the phase plot, see what is the corresponding frequency. I think for both it is 5 radians per second. So the conclusion is, in this particular problem, both frequencies are 5 radians per second. So students, please try both these problems before we start the next session in Bode plot. Okay, so you have to draw it and see, otherwise you will not get a hold on to this Bode plot. Okay.